Hello, I'm going to briefly describe how you install OGhidra, use some of its features, and the differences it has with kind of OGhidraMCP. So after you've cloned the repository, you can run pip install r requirements. After you've installed these requirements, let's go ahead and clear this page. You want to open up your instance of Ghidra. I believe this works for any version of Ghidra past 11.34, I believe, but your mileage may vary. So like with OGhidraMCP, you want to install it as an extension, um, which I've added into the main repo. So there's this OGhidraMCP.zip. The primary difference of this is that it adds the ability for the AI to scan raw bytes within memory. And then you'll restart Ghidra. Which should load up the plugin. I've selected a sample binary here, which should have some malicious features, but is not necessarily malicious. And we're going to see whether or not the AI is able to kind of agentically reverse engineer this without any assistance and determine if there's any malicious behavior. So with everything installed, we can just run python main.py-ui. There's a CLI version as well, in case you want to strap this to another tool. So here's the new UI for OGhidra. I've kind of went with the darker scheme. It's easier on the eyes. Some things we'll notice is that it's only one table. You can simply track your workflow on the right here. Um, and something I want to show you is that, if you want to use your own local models to prevent any concerns with data loss prevention, you can. Currently, I'm using a cloud-hosted model that's running on my Ollama server. So all that's required are a series of embedding models and a cloud model if you so wish to choose. You can test this connection here. It basically just pings to your Ollama server and whether the OGhidraMCP is connected. Go ahead and save that. Since I'm using a cloud model, this should run pretty quickly. So we can ask it a basic question like, here it'll go through kind of its agentic steps, which is kind of the planning phase, the execution phase, analysis phase, and review. Something I've added is allowing it to actually print out the chain of thought through each step. So you can kind of track what's going on and why the AI performs a certain action. Something I've also wanted to mention is that we can see here that the execution loop for a single agentic cycle is minimized to 10 steps. You can customize this and switch this to in the .env file. This is basically just how many rounds of react, so reasoning then action, the AI takes per an agentic cycle. And then you can also have a larger number of agentic cycles if you have more complicated tasks. But I've reduced this to try to focus on kind of smaller agentic tasks that the AI can help out with. I find that 10 steps and 2 loops is enough for many actions that a reverse engineer will typically want to take. So some things to note, we can see that some of the few tool calls that it's already made is to first list the imports. Oh, and it's searching for a series of strings, which is interesting. Um, First listing imports, listing exports, and then searching strings to not make it too easy for the AI to determine what this binary is. Actually, I've kind of changed the name of the file to kind of limit what it can actually look for, but it's still probably able to find key information from the strings. So now that the AI has kind of finished with its agentic steps, it's correctly determined that this application is actually just PS password from the sysinternals utility. We can kind of see what information it's done to grab to determine this. It's described kind of like the file characteristics, whether it's a PE file or if it's a 32-bit file. It's described some of the network operations used, and we can kind of see that it's already kind of determined that the licensing information is part of that sysinternals. So that probably gave it a huge hint. So with that, it can probably scope that it's not malicious, but it's a legitimate software called PS Password. Next, what I wanted to show is how to use the RAG feature within OGhidra. So what the RAGs really allow you to do is semantically retrieve any function that's relevant to your user's query. How it works, like any other RAG, is that the AI first goes over every single function and kind of comes to generates a quick analysis summary. And with that analysis summary, it goes into an embedding vector. How that works, we'll take a look. So here I have a very simple binary, curl.exe. And as we launch our tool, I will load a previous session where I've already analyzed all the functions within um, the curl application. We can see for each one, we'll see the name of what the function used to be, what it's been turned into, as well as its address and some description about what the function does. With this information, we can kind of run load vectors, which turns each of these summaries into an embedding, allowing us to kind of retrieve it for later. Once the vectors get loaded in, we can kind of check our system info, see if these functions actually get added. So we can see that these 299 functions have been added as embeddings. And then we can go ahead and ask very specific questions about each individual function, like, can you find me? So the primary value of doing this RAG embedding process, even though it's very cost intensive, is that when you're dealing with kind of difficult search space problems, like trying to find a specific function or a specific behavior within a binary, it can be very difficult for the AI to try to um, determine where that is, purely based on reverse engineering and taking like slow agentic steps. By fitting it into a RAG, we do this kind of semantic retrieval that is also helps the AI navigate as well, and kind of provides a map of where everything is. Um, because each one of these functions is already renamed and it's already given a kind of a semantic analysis of what is going on. So with that in mind, it's able to quickly find us this one parse cookie header within this address, and very aptly describes what it does and where it's found in the binary. I hope that helps. Thanks for watching.